Hello everyone, so today we'll be solving a problem from Gauss's law from electrostatics. The problem is as follows. The region between two concentric spheres of radii A and B respectively has a volume charge density as rho is equal to A by R, where A is constant and R is a distance from the center. So what is happening is there are two spheres of radii A and radii B, and the region between these two spheres has a material with a charge density as A by R. Please note that the charge density is dependent upon the distance from the center. It is inversely proportional to R. So the charge density is higher as the radius, if the radius is low, the charge density is lower as we go away from the center. Okay. Okay, so let's move ahead. What it says that uh, the value of A such that the electric field and also at the center of the sphere there is a point charge Q. The value of A such that the electric field in the region between the sphere is constant. So we have to find out the A such that this field over here is constant. This field between this everywhere over here is constant. So field is constant, it is given. So what did this mean? The field over here, field over here, field over here, everywhere it is constant. That means field at this surface of a sphere of radius A is same as the field at this surface of the sphere of radius B. Okay, so this is what it means. So let us start at this point that EA or what it is called at the electric field at the surface of sphere of radius A is equal to electric field at the surface of the sphere of radius B. What is EA? EA is nothing but the electric field at a radius A. What is the electric field at a radius A? We can see inside the sphere of radius A or inside the Gaussian surface, there is point charge Q only. That means electric field at A will be only because of Q. This is the Gauss's law. So electric field at a radius A will be nothing but 1 upon 4 pi epsilon naught. This is standard formula Q upon A square. Okay, this is a standard formula of a electric field at a distance A from a point charge. How to find electric field at B? Electric field at B, to find out electric field at B, now we can see if I draw a Gaussian surface at a radius B. Okay, if I draw this Gaussian surface on the boundary of sphere B, what is the charge included in it? What is the charge enclosed? The charge enclosed is this point charge and this charge because of this volume charge density. Okay, the charge because of this point charge and charge because of this volume charge density. So if I apply a Gauss's law, what is the Gauss's law? Let us write it down first. So Gauss's law says the electric flux through the Gaussian surface, the electric flux is written as E bar dot ds bar integrating over that surface is nothing but equal to charge enclosed in that surface upon this constant epsilon naught. Okay, so for Gaussian surface, this Gaussian surface, what is this left hand side? For this Gaussian surface, left hand side is EB. So instead of E, there will be this EB, and EB is constant on this surface. So EB I taken out and I will have to integrate over ds. ds is nothing but, if integration over ds is nothing but the total surface area of that sphere of radius B, which is nothing but EB into 4 pi B square. Okay, so this is the LHS what we got. And what is the RHS? RHS is nothing but Q upon epsilon. Please note that this is not this Q, this is the total charge enclosed inside the Gaussian surface. So to avoid the confusion, let me just denote it by small q. Okay, so the flux through the Gaussian surface is nothing but the total charge enclosed in that Gaussian surface upon epsilon naught. Okay, So in this formula, we have calculated what is LHS is. Let us try to find out the total charge enclosed in this sphere of radius b. The total charge is 1 upon epsilon naught. And what is the total charge? The total charge included in this sphere is the point charge q plus charge because of this shaded region. The charge because of this shaded region. Okay. So since this is a charge distribution, let us first find out what is the charge inside the shaded region. Please note that the volume charge density is given to us. Okay. So usually what is a charge? Charge is nothing but the charge density into volume. And since the charge density is varying with the distance, we have to integrate. So how to calculate that? So first, let me draw a sphere, a spherical shell inside this shaded region of radius r. So this is the radius r. And let us also draw another spherical shell a minuscule distance away from this original spherical shell of distance r. Okay, so this distance is dr. So this is a small thin spherical shell. Okay, so what is the charge enclosed in this spherical shell? The charge density ar into the small volume, the small whatever the volume of this spherical shell, which is 4 pi r square, the surface area into the small thickness dr. Okay, now we move this shell from A to B so that we will get the total charge in enclosed in this spherical in this shaded region. So we will vary this integration from A to B. Okay, so we are traversing this small spherical thin shell of width dr from A to B. So this will get me to total charge in this shaded region. We can see this r and one r gets cancelled. So I will have 4 pi a r dr from A to B. What is the integration of r? 4 pi a r square by 2 from A to B, or 4 pi by 2 b square minus a square. Okay, so I calculated q shaded. So I know my RHS. So my RHS from in this Gauss's law is 1 upon epsilon naught q plus, sorry, here a is missing, 4 pi. We can just do this 2 to the 4. So it will become 2 pi a b square minus a square. Okay, so clear. So this is LHS that we already obtained, and this is RHS. What we wanted to do, why we are doing this, to find out EB. So let us do LHS is equal to RHS and find out what is EB. And if I get that EB, I will just equate it with EA. Okay, so on equating LHS, which is EB 4 pi b square, with RHS, which is 1 upon, sorry, this has to be capital A. So 1 upon epsilon naught, RHS is q plus 2 pi a b square minus a square. Okay, yes. So what is EB I get? EB I get is 1 upon 4 pi epsilon naught 1 upon b square q plus 2 pi a b square minus a square. Okay, so I have EB, I have EA. Now I will equate these two because this is what the given condition is, and using that given condition, okay, so I also so using that given condition we can find out what A is. Okay, so let's equate EA is equal to EB. What was EA? 1 upon 4 pi epsilon naught Q upon A square. 1 upon 4 pi epsilon naught Q upon A square. Okay, is equal to this EB is this whole expression. 1 upon 4 pi epsilon naught 1 upon B square Q plus 2 pi A B square minus A square. We can say this 1 upon 4 pi epsilon naught get cancelled, and what we can do, we'll just simplify it further. Q upon A square Q upon B square plus, let us put this B square inside, 2 pi A B square by B square minus A square by B square. So this will give me 1. Okay, simplifying it further, Q upon A square is equal to Q upon B square plus 2 pi A minus 2 pi A square by B square. Okay, so yeah, 2 pi A will be here also. So yeah, at the end we have to find out A, right? So what we will do, so let me just erase this step. We want A, right? So we want this. So we will subtract q by b square from both sides. So we will have q square by a square minus q square by b square is equal to 2 pi a 1 minus a square by b square. We can cross multiply it over here. So I will have b square divided minus a square upon b square. Okay, and here also I can take out cube common, b square minus a square upon a square b square, 2 pi a b square. So b square will get cancelled. B square minus a square and b square minus a square will also get cancelled. So what we will have, q upon a square is 2 pi a, or which implies a is equal to q upon 2 pi a square. Okay, so I guess this will be in there in option q upon 2 pi a square. Yes, so option number 1 is correct. Of course, using this variation of the charge density and other factors, you can also get this answer. I can at least eliminate few options over here, but this is the method to solve this problem using the Gauss's law. So thanks for watching this video. I will see you in the next video.